The growth rate essentially can be influenced by a variety of circumstances, resulting in a wide range of growth patterns. For example, the first one was simple, linear population model, then the logistic growth rate. So in general, we find a lot of growth rates. For example, Malthusian growth rate, logistic growth rate, food limited growth rate, compost growth rate, etc. Among these, the logistic type growth rate is simple and quite reasonable from ecological point of view. It may not work all the time, but it is fair enough for many of the ecological species. So many of the researchers have used logistic growth type growth rate, but there are other models also which have been used in the literature. Yeah, next one, please. Now, this was one species. Now suppose there are two species, then there would be interaction. And what we are talking about here is the prey-predator model. That is, there is a prey and there is a predator. So how do they work? So the general idea of the prey-predator model is to consider an ideal scenario in which that only two species coexist: the predator, and their prey. To model a prey-predator model, we make certain assumptions, because in modeling we always do some assumptions, and under those assumptions, under those restrictions, we try to study the problem. So the predators can survive only on the prey population. They have no other resource for their survival. So all the time they will depend upon the prey population. The total amount of food consumed by predators per unit time is proportional to the number of attacks on the prey population by predator. So that means the amount of food which is available is the how much predation has been done with the prey population by the predator. The number of attacks by predator on prey population is proportional to the size or density of both prey and predator. That means it is proportional to both. That interaction, whatsoever is taking place because of the predation, is proportional to the size of the prey as well as the size of the predator. Each predator needs a minimum amount of food to survive and reproduce. Each prey has an unlimited amount of food that helps it to reproduce in the absence of predators. So that means prey can, prey can have unlimited amount of food. So there is no restriction on that, and it can reproduce in abundance. So therefore, predator will survive only on prey. Prey has other food on which it will survive and keep reproducing it. Yeah. Next one. I have given the references below. If one is interested, can have a look at that. So in general, the certain assumptions, we can write down that if n is the population of prey and p is the population of predator, then the rate of change of prey is nothing but the growth rate of prey population in the absence of predator. So first term here is when there is no predator, it's just growing it. And similarly, when you talk of the predator population, the first term here is because there is no interaction, it is not catching the prey. So it is declining rate of predator population in the absence of prey, because then it does not have any food. So the rate will keep declining at that stage. So the second terms in Buddha cases essentially talks about the interaction between the prey and the predator, that how much predator catches, so the total capture rate of the prey by predator. And second term in the predator population is contribution of eaten prey into the growth of predator. So this is what contributes at that stage. NT and PT can denote the current population densities of the prey and predator respectively. Yeah, next one, please. Now, the second, we talked about the populations. Now, We can also have more populations, but we will more or less restrict to populations. Then the third term which comes here is what is harvesting. Harvesting essentially is a removal of individuals from a population for various purposes. For example, it could be agriculture harvesting, cutting trees for paper production, etc., etc. Fisheries harvesting, wildlife harvesting, forestry harvesting. For example, removal of specific trees for the growth of other trees. Fisheries, of course, we know that fishing for commercial purposes, etc. So we have different reasons for the harvesting. These are just listed some, but there can be more. By the way, I'm audible clearly. Am I audible clearly? Okay. Next one, please. Then why do we need harvesting? As I said earlier, the scenario requiring harvesting is that harvesting becomes necessary when population exceed the carrying capacity or resource utilization. So suppose the resources are not enough, so you remove some of the population from the given. Then balancing it, which is very important. It involves balancing of resource utilization to meet the human needs with the conservation of species and ecosystem. For example, when we take out, we harvest fish for the consumption for the human population, but there has to be a certain conservation of the species also in the ecosystem. Therefore, a balancing act is very important. There could be a selective harvesting, that is, you target only specific individuals or species for removal. Non-selective harvesting is very dangerous, remove individuals without any discrimination. Or the most important is sustainable harvesting, that is, harvesting that ensures population can regenerate and persist all the time. So from sustainable point of view also, the harvesting is very important. Next one, please. Importance of harvesting we have already seen, but from the research point of view also, it is very important because one would like to study the behavior and the biology of the population dynamics. Therefore, a lot of scientists have tried to understand the ecological relationships which which can be informed to the conservation and management strategies. It is important that the motivation for harvesting is a predator-prey model should ideally consider ecological sustainability, ethical considerations, and long-term health of ecosystem. Long-term health of ecosystem is very important. That means the both predator and prey survive, and it should not depend. That means the population is not depleted to the point of endanger and endangerment, and that the ecosystem remains in balance, so that there is no danger to any of the species, and the system remains in balance. This is what should be the aim of the study essentially. Yeah, next one. So mathematically also we would like to see what type of harvesting functions could be there. One is, of course, constant harvesting. That means you keep on removing at a rate which is constant. And second one is a slightly more interesting. That is proportional harvesting. That is the harvesting is proportional to the population of the species which is being harvested. So this is H1xe is equal to Q into E into X, where Q is the catchability coefficient, the way you catch the thing, species, and then E is the effort applied to harvest individuals. Next is nonlinear harvesting, which is given by H2X E that is this one, where QEX upon M1X plus M2E. So the both effort and the populations are involved. So this involves selective removal of individuals from a population based on certain characteristics. We can have this has several advantages over the linear harvesting. where a fixed population of is harvested indiscriminately. For example, if you see the first one, this uh, proportional harvesting, if population keeps increasing, harvesting will also keep increasing. Or if the efforts are high, harvesting will also be high. It doesn't happen the same in the second case. For example, if the population is very high, then it reaches a certain, it is not indiscriminately done. It it is it goes to a certain limit and it stays at that stage. So nonlinear harvesting shows the preservation of the age, size, or sex structure of the population. I've not shown it here, but this essentially is the meaning there. This can help them. This can help maintain the diversity and stability of the population, which is often disrupted by the linear harvesting. So this proportional harvesting has certain limitations, and this is more meaningful. But we will talk about all the three possible cases in our discussion because we are just giving the glimpse of various harvesting population models here. Next one, please. Next one, please. Yeah. So I will start with the one species model with harvesting. So Clark and Schaeffer proposed a one species fish population model that is growing logistically and that is being harvested with a population with a population, sorry, proportional harvesting. So if let us assume that the catch fish per unit effort is proportional to the stock level n. So n is the population of fish, and we are using proportionality harvesting. Then the first term here in the rate of change of population, the first term essentially is the growth rate of the population, and second term is the effort applied or the catchability or the harvesting effect with the effort E and catchability Q. We have already said what R and K are there. Harvesting rate is E. If in the harvest rate, E represent the fishing effort and Q the catchability coefficient. We have so if we study the now I'm coming sort of mathematics here. If we try to understand the what is the steady state values, so that means the dn by dt equal to 0. That is after a long time, what can be achieved here? It says that either n star is equal to 0 or n star is equal to 1 upon 1 minus q of qe upon r. So both these possibilities can exist after a long time. So the steady state n naught equal to 0 corresponds to extinction of the stocks. That means there is no population ultimately. However, in that case, for small values of the fishing mortality, steady state n star is asymptotically stable. And it is clear from this figure, the figure 1, not 2. It is clear from figure 1 here that, for example, if this is there, dn by dt is here, and this is n we are talking about here, n equal to 0. So if this is positive, it will keep growing. It will keep growing, and therefore this will be stable. While if n star is here, at certain, I mean, this, if qen is greater than this parabolic profile, the value is greater than this, therefore this will move this side, and from here this will move this side. You go to the previous slide, just go to the previous slide. Yeah, if you see this, in case qen is greater than this quantity, this will become negative, and therefore it will start decreasing. In case this is positive, then if this is greater than qen, then this will be positive, and therefore this will keep increasing. Next one, please. If you see it here, in case this is positive, this is greater than this quantity, this will move, the whole thing will be negative, and this will keep moving this side. And from here, it will become positive. So this will keep coming here. So this is stable quantity. Yeah. Next one, please. So in both the instances, perturbation decay and the stock level returns to n star as suggested by the arrows shown earlier here. So in any case, this will keep coming here. However, the steady state is in turn is unstable. So we will again we start increasing the fishing mortality. Then steady state and start shift to the left, but still remains. So in case the efforts are more and more, so it shifts to the left, but n star is still there and it's still stable. Next one, please. Next one, please. Yeah, that's fine. So if we still continue to increase, yeah, if we continue to increase the fishing mortality, it eventually comes to a point where the harvest exceeds the growth rate. If you see it here, it exceeds the growth rate, and the harvest exceeds the growth rate for all positive stock levels. Suddenly, the steady state at the origin becomes stable here. So corresponding to extinction, this is corresponding to extinction, it becomes stable. So there's only one uh, steady state point. In case the efforts are too many, very high, there will be only one steady state point, and this will be stable now. Next one, please. This is called as a severe overfishing. So if you see at this stage, what we basically see is the location of a steady state as a function of fishing mortality. This is n star is there, so this is essentially stable. The light line, light line shows the stable one, and the dark line shows the unstable one. So if we start go beyond n star becomes negative. So biologically, it does not make any sense. But just to give a feel of mathematical result, at this stage, it becomes unstable, and this zero becomes stable. So there is a change of stability, and this leads to transcritical bifurcation. Yeah, next one, please. Sustainable yield is again important. I think I will skip this. Next one, please. Yeah, next one, please. So far we have considered only logistically growth rate population. However, some population possess a threshold to growth. So they cannot keep on growing like this. There will be a certain threshold for this. So a simple differential equation model is dn by dt is equal to rate of change of population is nothing but r into n upon k naught. So there is a threshold with k naught minus 1 and 1 minus m by k. So this essentially gives us a type of this dn by dt looks like this as given in the figure 6 here. So there is a threshold k naught, and solutions with initial conditions above k naught approach the carrying capacity. Before that, they go to 0. So initial condition becomes important at this stage. Yeah, next one, please. So this for such population models with proportional harvesting, we obtain two equilibrium points or the steady state point, and n star is plotted here. This is not constant. This is the population harvesting here. So one is stable, this is unstable, and this is unstable here. It generates a bifurcation, and at some point they collide. Yeah, and this leads to a saddle node bifurcation at this. So this essentially leads to a saddle node bifurcation. Yeah, next one, please. Now I come to a two species prey-predator system consisting of with constant harvesting to start with. So this is Michaelis Menten type predator prey model. So this is essentially the logistic growth rate. This is a non-linear harvesting. Sorry, this is non-linear interaction between the prey and predator, which comes here, and this is again death of the population model here. So Xiao and Jennings proposed a constant type of prey harvesting at this one here. So this is a constant rate harvesting here. Yeah, next one, please. So as the values of the parameters of the model vary, a numerous kind of bifurcation such as serial node bifurcation, subcritical and supercritical hop bifurcation, Bogdanov Tekens bifurcation, homoclinic bifurcation, heteroclinic bifurcation, etc., are being shown. So it gives a very variety of bifurcations are seen here. So mathematically, it becomes quite challenging to work with this model. Yeah, next one, please. Another one, in the previous one, there was a constant harvesting in the prey, but in this case, there is a constant harvesting of the predator. So the obtained results reveal a richer dynamics compared to the model with no harvesting. Suppose there is no harvesting, it shows much richer dynamics here and different dynamics compared to the model with non-zero constant rate prey harvesting here. That means in case there is a prey harvesting, it shows different results from that also there. Now I come to another one, two species prey predator system with constant harvesting in both the species. So there is a harvesting here, there is a harvesting here also. There, this is of course the interaction, the predation taking place. Phi is a certain function which we have seen earlier, and we can work on that. So C is essentially nothing but the conversion vector. That means whatsoever is eaten here. Sorry, next one please. Next one please.
Yes,
Next one please.
yes,
Yeah,
Prof.
just previous one. Sorry, just previous one. Yes. So here, if you see, there is there is a constant harvesting in both population, predator as well as prey. The phi n is into P essentially tells us the predation taking place, A into phi n into P, and C is essentially the conversion vector. That is whatsoever is available, how much is being taken by the predator. So yeah, next one. So it gives us very nice results. If the harvesting is at a rate where no equilibria exists. So basically, it is possible that there is no equilibria exists for certain values of various parameters. Then the extinction of both species will result. So ultimately, they will both vanish. On the other hand, the existence of equilibria may not be sufficient to guarantee the biological resource stocks would not be exploited too heavily without an ultimate loss of productivity. Second outcome is that a detailed examination of the dynamical behavior in the vicinity of the equilibria indicates that even though the system has two equilibria interior to the first quadrant, the system possesses only a set of measure zero on which both the species coexist. So the coexistence is on a very small set. If this happens, the coexistence may be impossible in real life since it is extremely susceptible to collapse under small perturbations. The dynamics exhibited by the system show good consistency with the observations in the biological reality. If the unharvested system is unfairly persistent, uniformly persistent, then the sufficiently small harvesting rate will not change drastically. So these results give a theoretical support to the safe harvesting in biological resource management. Yeah, next one, please. Yeah, I think I can skip, go to the next one. Now we consider constant harvesting, mm, then we consider linear harvesting. Now we are considering non-linear harvesting. Yeah, we are considering linear harvesting. So two species predator system with linear harvesting and predator. Sorry, this is again, uh, there should be something more here. QE, N should P should be there. Yeah, in the equation, second equation, there should be a linear harvesting should be shown there. So E is the external effort external effort devoted to the predator harvesting and B naught be the conversion effect efficiency of the author. So we can see that it gives a qualitative analysis shows different outcomes, including switching of stability, oscillations, and deterministic extinction. Next one, please. I'm cutting it because of the time availability. Yeah. So this is linear harvesting in both the species here. So this was given by Carr et al. 2006, and this very interesting paper. Here what is more interesting is that there is a functional response to the predator which shown Holling type 2 response function. The second term on the first and the first term of the second one, it essentially says that there is the model incorporates a refuge protecting the prey. For example, here all the whole population of prey is not available for the consumption. There is a refuge for the population, and therefore not everything is given to the predation. This is what is interesting here. Next one, please. Uh, Gupta et al. They consider a two-species competition model with combined harvesting. So again, there is a harvesting for prey as well as predator population. There is a sort of competition between the two harvests, two populations. So what it says is that there is a presence of toxic substance which restricts the growth of the other. So the third term essentially here, if you look at in both the terms, if you look at the third term, this is giving the idea of the toxicity of one to the other here. So the constant A R1, Ki, alpha I, and gamma I respectively denote the intrinsic growth rate, carrying capacity, coefficient of interspecific competition, and toxicity coefficient for the ith species. Next one, please. Then we have two species prey predator model with nonlinear harvesting. So here we are considering the nonlinear harvesting, and both of them, please note here, there is a change in the population of predator. It is not exactly logistic type, but it is something like logistic. So here what it says that A1 is the maximum value of the per capita reduction rate of prey and measures this small a which is coming here in the second equation. It measures the uh, extent to which the environment provides protection to the prey and predator respectively. So it provides protection to both predator as well as prey as well as the predator both. And then rest of the things are essentially same. So it's slightly different from the previous ones, but it is interesting. Yeah, next one, please. So now this is nonlinear with the predator one. So there is a predator. In the predator, there is a nonlinear harvesting which is taking place. Next one, please. So far, we have considered the effort is constant. E is always constant. But in certain cases, E is not constant. For example, when you have open access fishery, where fish population depends partially on resources with functional responses, it is assumed that the dynamics of resource biomass and fish population, PT, the N is biomass and P is fish population. So N is resource and P is fish population, follows logistic growth rate, and then fourth is dynamic. It has a dynamic harvesting of food. And to conserve the population, for example, the regulatory agencies will impose a tax if the biomass of the fish exceeds a certain limit. Therefore, keeping in this view, this of course the predator is there and there is a harvesting term QEP in the predator. But then last equation is essentially talking about the effort being dynamic here. E depends upon the time. So P minus T essentially If the penalty P is a small p is the penalty, if Px is more than tau, which is the critical value, then this will be a positive quantity. And then one can basically look how it is going to. So this was a slightly different type of prediction model which was done. Next one, please. Yes, this is a three species prey predator scavenger system. Scavenger system is that those species which survive on the dead prey or predator system or population. So Z here is the population density of scavenger, and then other is prey and the sorry next one please. Yeah, this is okay. That's fine, 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 fine. Just go to the previous one. Yeah, that's fine. So if you look at the third equation, this is the equation for the scavenger, and that this is what it says that whatsoever is dead, it essentially works on that. So beta 1 and P essentially is essentially predation taking place, and from that, whatsoever is dead, it consumes part of it, and similarly, it consumes part of the population P population also. So here Z is the population densities of the scavengers, and the rest of the thing is given. Yeah, next one, please. Now it is slightly more different when it considers quadratic harvesting. Earlier we were talking about linear harvesting, etc., but now it is quadratic harvesting, which has been seen here. The last term here, H1 P square and H2 Z square essentially talks about the quadratic. Yeah. Next one, please. Now, this is again a model which was given for omnivorous top predator. That means it eats both prey as well as predator, and there's a non-linear harvesting taking place for the predator. Next one, please. Basically, just to come to the time uh, limits, I'm looking for certain results only. I have not given everything here, just talking about certain things. So we need to consider I have just given few models, but there are many more models which are available here. There are several important contributions and developments in the field of predator prey models with harvesting since Lutka initial model. Some key contributions and notable developments are sustainable and optimal harvesting. Harvesting controls rules. For example, scientists and policymakers have developed various harvesting control rules and management studies based on predator prey models. These rules aim to provide guidance for regulating harvesting effort to prevent over exploitation and promote ecological sustainability. I just put it here because this is what is more important. Next one, please. We need to consider the spatial considerations. We have not considered when the migration from one place to the other place taking place. So this includes considering the how harvesting in one area affect the population in neighboring regions. They are important for understanding the movement and dispersal of species in response to the harvest. We have considered only the deterministic model, but stochasticity and uncertainty is also important. Then the last one, of course, the next one is when you have multiple species and how do they behave for the harvesting of different populations. Next one, please. Then economic perspective is also important. We have to integrate economic principles into predator-prey models with harvesting. This includes incorporating cost-effective, cost-benefit analysis, discount rates, etc., etc. And ecosystem-based management. The concept of ecosystem-based management has gained importance and prominence, which emphasizes the need to consider the broader ecological context when designing harvesting regulations. Predator-prey model are used to understand how harvesting impacts not only the target species but also the entire ecosystem. Next one, please. So, concluding the whole thing, I would like to emphasize on the rich dynamical behavior of these models. Ecological model, from mathematical point of view, also there is a very challenging, and therefore I would just like to point out this. So, ecological model offer a fascinating lens through which one can explore dynamics of natural systems. The study of ecological models has revealed a wealth of rich and complex behavior, providing profound insight into the natural world. These models have shown us the ecological systems are dynamic, ever changing, and often unpredictable. From stable equilibria to integrate oscillations, the dynamical behavior of ecological models is a testament of the complexity of the nature. Understanding this rich behavior is crucial for informed conservation management and decision making is in ecological context. As we continue to explore, analyze, and refine these models, we will be uncovering more about the integrate tapestry of the life in our planet. Let us embrace the challenges and opportunities. I mean, this is just the hope that the dynamics of ecological models present us as we strive to protect and preserve the beauty of balance of our nature. Well, I would like to acknowledge with thanks Dr. Ravi Gupta. He did PhD with me, and now he's assistant professor at BHU. Essentially, he worked for these models during his work. So, thank you. So the idea here was just to give a glimpse, not going in the details, but just to give that how important it is and then how it works. Thank you so much. For details, one can see the papers which have been listed there.